and the Responsible AI Conference. And as we all know, artificial intelligence is developing very fast and is playing an important role in our lives. And in spite of the great success and advancement, it is imperative to prioritize the trust and responsibility in its development and deployment. So this is crucial to ensure their safety and potential risks. And therefore, the trustworthy and responsible AI has been gaining considerable attention in past years. And from the academia to industry, from government to scientific community. So this platform, this conference will serve as a platform to share the cutting-edge knowledge and insightful new views in this area, in this timely domain. And we have the privilege of hosting renowned experts, scholars, and professionals to deliver keynote talks and engaging panel discussions. We hope through this event, we aim to foster a deep understanding to the challenge and issues and opportunities lying ahead. And also, we want to create opportunities to establish and strengthen our partnership and collaboration. So let's work together to explore the critical dimensions of AI that will shape our future. And finally, I would like to express my sincere gratitude to our esteemed speakers and honorable panel members, including Zoe, Alexandra, Helena, David, Richard, and Sebastian. They are the keynote speakers and panel members in the morning. And also we have the Alexandra, Caroline, Lucas, Miguel, Blaze, and Mary in the afternoon. Yeah, we also would like to thank our supporter, including Cambridge Center for Data-Driven Discovery, Kavli Center for Ethics, Science, and the Public, and Cambridge Global Consulting, AI at CAM, Center for Human-Inspired AI, and BitFund. So they have dedicated their invaluable time and effort to make this conference possible. And to all the participants, your presence here are the greatest support to us. And we hope you actively engage in the discussion in the conference and network with fellow attendees. Yeah, once again, thank you for coming and hope you enjoy the conference. Thank you. Now let me hand over to the session chair, Lefan Wang, will introduce our speakers.
Good morning, everyone. I'm Lefan. It's my pleasure to chair this session. I'm a postdoc working at the Department of Engineering at the University of Cambridge. So our first speaker in this session is Professor Zoe Kourtzi. She's a professor of computational cognitive neuroscience at the University of Cambridge, a fellow of Alan Turing Institute, and a fellow of Royal Society Industry. Aims to develop predictive AI-guided models with a particular emphasis on neurodegenerative disease and mental health. Her work holds a great potential for early diagnosis and personalized interventions. Today, she will share about her insights on robust and interpretable AI-guided tools for early dementia prediction. Please give a warm welcome to Professor Zoe Kourtzi.
Wonderful. Good morning, everybody, and thank you very much for the really kind introduction and for inviting me today to tell you a little bit about our work. What I wanted to talk to you about today is a big effort we have in the lab with my team in terms of taking AI and translating all the way to the clinic. And so I will run you through our both research and implementation work, so both development and implementation. And I will focus particularly in the aspects that have to do with responsible and interpretable AI. So as you heard, we work in the space of brain and mental health disorders. We focus on neurodegenerative disorders. I will be talking to you today about the challenge of dementia. At least 1/3 of all disease burden comes from neurological and psychiatric conditions. Dementia recently has become the leading cause of death in the UK, and there's growing mental health crisis, especially in young people. So this is a huge need, a huge societal need that we are trying to serve through our research. Now, we are really at critical times, not only because of the need, the societal need that neurodegenerative disorders impose, but also because of the tools that have become to us available in science. So the last 2 decades, we had 2 revolutions. In 2000, we had the resolution of brain imaging, which allows us in a non-invasive way to look at the human brain and its workings. Now, in 2010, we saw a revolution in artificial intelligence and data science that gives us really sensitive and powerful tools to be able to understand how the human brain works and what happens when things start going wrong. So the big question for us in my lab, in my team, is how we harness these revolutions to impact brain health. So we operate on 3 principles, and our vision really includes these 3 points. One is we are looking for building models that they are biologically informed. So we care about how the brain works and why things go wrong. Therefore, the models we build, we ground them in biology. Next, as also really important for this symposium today, we need these tools that we build, we need these models that we build to be interpretable. We need to be able to interrogate them and gain a mechanistic account about the brain, about disease, so that we can intervene. And finally, we need these tools that we build through AI to be interoperable. And the reason for that is we deal with global health challenges. Dementia and neurodegenerative disorders are global challenges. It's not something that we encounter only in Cambridge or in the UK. So therefore, it's not good to build local solutions. We need to build global solutions, and therefore our data, our models need to be interoperable. So today, as I said, I'd like to show you the first success story that we have through dementia. I should say already that this is really a very much cross-disciplinary effort, a really large team of computer scientists, engineers, mathematicians, cognitive scientists, neuroscientists, clinicians, research engineers are involved in making this happen. So me standing here today is really represent the work of many people. So as we said, the need is huge. Every 3 seconds, someone is diagnosed with dementia, and 50% actually of individuals with dementia remain undiagnosed. We also know that the causes of dementia start in the brain 10 to 15 years before symptoms occur. Therefore, we have a window that if we can predict early and reduce misdiagnosis, which currently at that early stage is about 20 to 35%, we have an opportunity to make a difference. And of course, if you go into the Alzheimer's Research UK website, you will see the numbers are really stunning in terms of what we expect, 1 billion people by 2025 living with dementia. So we focus in early detection, specifically for the reason that I mentioned. Symptoms appear 10 to 15 years after actually the disease starts in the brain. So we do have an opportunity in that window if we can build models and tools to predict early. And if we can also predict precisely, we can intervene. First, that helps us understand the disease process better and the interactive factors that bring along symptoms. It allows us to do precise patient stratification into the different disease subtypes, and this way we can encourage lifestyle interventions that we know can make a difference, sometimes all the way to reducing symptoms or to prolonging the period until when symptoms might occur, and finally design personalized treatments. Now that's where usually I get the question of, well, what is a good detecting early if we have no disease-modifying treatments? Now, this picture has really changed this year. Since November, we've already seen 2 dementia-specific drugs being approved by the FDA, making difference to symptoms, not only making differences to the brain in terms of changing the picture of the brain, but actually changing symptoms. This might not be yet the best, but they are the first, and they are really promising. And I think lots of us are confident and watching this space very closely in terms of how quickly potentially this space can move to disease-modifying treatments. And if you look back in the news, the first thing that came out when these drugs came out, all the excitement, the first comment was, if we can detect earlier potentially disease-modifying treatments coming forward, we'll be able to be more effective. So this is really why we work in this space, to make the diagnosis more precise and therefore make personalized treatments more effective. So let me show you the challenge. Usually we diagnose dementia with MRI scans. As I said, we harness this revolution of brain imaging technology. And these are two structural MRI scans. And potentially you'll be able to tell by looking at these pictures which one is a healthy brain and which one is a diseased brain. Who thinks the brain on the left is healthy, the brain on the right is a diseased brain? Excellent. So this is an easy, really, discrimination to make. You see the quite large ventricles here, an atrophy in the brain that indicates potential signs of neurodegenerative disorder. The difficult thing is actually a brain like this. Now, this is the brain of a patient diagnosed with mild cognitive impairment. Patients with mild cognitive impairment are at that very kind of early stage of disease. They'll potentially have some problems, primarily memory problems or confusion. They go to their GP. The GP will run through some scales, cognitive scales. The symptoms, kind of light symptoms, have been identified, and then typically the GP will refer to a memory clinic, and that's the first scan that people will have on the NHS. It's actually not very invasive. It does not require radioactive tracers. It's just an MRI scan. It takes 5 minutes on the NHS, and as far as brain imaging goes, it's the least invasive and the least costly. But as you can see, it's very hard to tell whether this brain is a healthy brain or a brain that potentially will progress to dementia. And that's where algorithms come in. That's where we come in, our team comes in. And what we do is we take research data, thanks to patients that have opened their data for research. And this is a huge thank you. We take research data that is multimodal. It comes not only from MRI scans and cognitive data, but also it includes genetic data, it includes biomarkers, for example, CSF or PET markers that are more invasive. It's a plethora of data, and we build algorithms that mine this data and learn from this data. Now, how do we build these algorithms? That's where really the craft of AI comes in, because we need these models to be, as I said, transparent and interpretable. So we build them with specific stages. In the first stage, we look really into extracting from the MRI scans biologically relevant features, clinically relevant features, features that have something to do with cognitive decline, which is a key characteristic of dementia. We then create models that try and stratify the patients based on quite fine discriminations. For example, these models don't look at whether an individual already has dementia versus they're healthy. That's something that any clinician knows how to do. What they look is at this very early stage of mild cognitive impairment, they ask the question of, can they detect whether somebody will remain stable or whether they will progress? This is where the clinicians need the model's help. In this very fine diagnosis where the MRI scan by the naked eye does not tell us whether a patient has already dementia or not. And finally, we don't stop in this classification because every individual is different. And of course, when we make these kind of binary classifications, we could have misdiagnosis. What we do is we move from this classification into an individual trajectory modeling approach, which means we map out the health trajectories of individuals, and we can see how fast or slowly they will progress in the disease. And that makes a huge difference for clinical pathways, and I'll show you a little bit. So let me show you some data. Let's start from the first step where, as I said, we extract features. So for example, we take the MRI images, and through PLS, we look for features that actually relate to cognitive decline. So we don't give the model everything. We give relevant, biologically relevant, and clinically relevant features. Then we validate actually these features. They clearly predict, as you see here, this gray matter derived score from PLS is in entorhinal cortex, an area that we know is hit by neurodegenerative disorders. and you can see it correlates with cognitive scores in different clinical scales, for example, the ADNI-MEM score or ASR. So these are validated markers that we give to the model together with some cognitive data. And then we ask the model to learn in a metric kind of learning fashion a space that allows us to separate classes. It allows to separate individuals that have mild cognitive impairment that will remain stable from those that within 3 years they will progress. I won't go into the details of the models, but I'm happy to answer questions. Now, these models, as I said, we build them to be transparent and interpretable. We can interrogate them and look at their tensors. We can look at the space they learn, and we can look at the different predictors that we put in. And then we can ask the question of which of these predictors carry more weight, which are the assays that potentially we need to be using to be able in the future to make the diagnosis better. And what you see here is we use gray matter from MRI scans. We use beta amyloid, that is a marker from CSF or PET. We use APOE4, that's a genetic marker. This we do when we train the models, and this is with research data. We did this using a large US-based database called ADNI. So what you see is that we get to separate reliably, actually this model separates reliably, stable from progressive MCI patients. And then we move on to ask the question of each patient is an individual, how will they progress? And what we do is we interrogate the model, and through a scalar projection method, we built a score that tells us about the prognosis of the patient. So it tells us whether an individual will remain stable or they will start moving away from that stable space and how fast they move away. And so we can build plots like this. This is all done now on data that has not been used for training the model. The model is now trained with all of these rich ADNI research data. We now start testing the model on independent data sets to validate it. And what we do is we go through the classification task, then we go through the trajectory modeling, the scalar projection exercise. We pull out this prognostic index that tells us where the patients are in this space. Are they stable? Are they progressive? Are they somewhere in between? And we relate this score, this prognostic score, to memory decline. And what you see is that the higher the score is, the higher the memory decline of the patients. And that starts giving us an idea about each individual patient, whether they will remain stable or whether they will move towards dementia and how fast they move. As you see, we do this for data that we kept out from ADNI, but we also do it with completely different data. Now, how do we know that this prognostic score is actually interpretable? Again, going back to can we interpret this? What does it mean? Is it clinically relevant? We validate this score by relating it against different biomarkers. As I showed you, first thing is we relate it to memory decline, which is a key profile of a characteristic of dementia. Then we relate it to beta amyloid, and you see the higher the score, the larger the accumulation of amyloid in the brain. The amyloid is a marker, is not highly predictive. We could have patients that have amyloid but not dementia, but is a good marker of dementia. We also relate it to atrophy in terms of loss of gray matter in the temporal lobe, and you see again that it relates nicely. And we look at APOE4, and we look at people that have positive versus negative APOE4, and you see that this score is higher in patients that have positive APOE4. Now, the interesting thing here is that all of these are markers of dementia, but each one of them is not conclusive, is not highly predictive. And the score we relate has come from looking at thousands and thousands of patients and their cases and integrating all of this data. So it's a more reliable, it's a more robust way of stratifying the patients. Now, I keep saying this, I keep saying it's more reliable in stratifying the patients, but what evidence do I have? And that's really the evidence we have. What we do here is to validate that this score that we get from the model now, this multimodal model has learned, has given us a score per patient. Does it predict the diagnosis of the patients? So what we do here, and this is still research data, we take the score for each patient. These are patients that we have not used to train the model, completely independent sample. And based on the score that the model gave us, we can put these patients in different categories. We can have patients that are stable, they have a very low score, patients that are slowly progressive or rapidly progressive. And then we ask the question, we open the clinical labels, the clinical diagnosis that these patients have been given. And what you see is that the patients that they are much more progressive are patients that have already been diagnosed as Alzheimer's. Okay, there's no surprise. Patients that they are early Alzheimer's are in the slowly progressive. Patients that have no dementia are actually stable, characterized as stable by the model. And here is the more interesting. These are individuals that are asymptomatic. They have no symptoms. They volunteered for research. They went through the same batteries and tests. And we look at their data with the model, right? These people are healthy. And the model says that a good number of these individuals will remain stable, but some of them will progress slowly. So do we need to be watching these people? Are we moving in that space of 10 to 15 years before disease symptoms where we need to be looking at individuals that the models are telling us that potentially they might be moving to disease, to a disease trajectory compared to a health trajectory. So this kind of seems like no surprise, but on the other hand, it really validates our models against clinical diagnosis. Now, the difficulty in dementia is what is the gold standard for validating the models against? Unless we have post-mortem, we really don't have good standards. But the best we can do is clinical labels and potentially tau, and I'll show you another example of the tau biomarker for validation. Now, the part that we are really, really very excited is this is not something that we keep in the lab. This has been fantastic. We've published our research papers, but we have a mandate to move this to the clinic. It's no good this staying in my lab. It has to see real patient data. And in collaboration with clinicians, Adam Brooks in particular, Tim Ritman, we have looked at memory clinic data. Now, these are patients that they have consented for research, but they are real patients. They don't volunteer for a study. They went to their GP because they had symptoms and they got referred to the memory clinic. They provide us their data and we give it to the model. And this is very simple data. There is no biomarkers here. The only thing we have is an MRI scan, this structural MRI scan, and some scales, some clinical scales. This is data collected in a memory clinic. So we train the model on this type of data and test the model on patients. This is patient data. And what you see here is we don't have actually the clinical diagnosis. We open the clinical diagnosis after we test the patient data with the model. The model will give us again the score, tells us some patients are stable, some are progressive. Then we open the labels. Patients are already diagnosed with Alzheimer's. The model says that they are progressive mostly. Patients that have been diagnosed with functional attentional problems, the model says these patients are mostly stable. They don't have dementia. They will not express dementia. Patients that have other neurodegenerative disorders but non-Alzheimer's, the model remain stable. Mild cognitive impairment patients, some of them are stable, some of them are progressing. And patients that simply have cognitive disorders, the model says they're stable. Now, you see all of this clinical diagnosis because these are real patients. This is not data, research data that is nicely stratified, where people are screened to go into the study if they have dementia or not. This is just people coming from all walks of life, ending up in the memory clinic because they have symptoms. But there is a lot of comorbidities. People could have, for example, depression, anxiety-related disorders, functional attentional disorders, other cognitive deficits that look like they have memory symptoms or dementia symptoms. And therefore, it's really important to put these models to be able to stratify them more precisely. So we have validated this not only at Addenbrooke's, but actually internationally with a collaboration in Singapore, where, again, we took data from a memory clinic. Again, this data is only test data, independent. We get the scores from the algorithm. We open the labels, and you see people from the quite far from here, the other side of the world. Patients with Alzheimer's, dementia, and vascular dementia are characterized by the model as progressive. Moderate mild cognitive impairment is either slowly or rapidly progressive. mild cognitive impairment, some of them potentially stable, maybe other comorbidities, or slowly progressive, and cognitive normal, most of them stable. Some of them we need to be watching. Now, the interesting thing about this data is they're longitudinal. In this memory clinic, we have data up to 6 years where patients have been followed. And typically, when I talk about this work, people will ask, well, okay, if you were to put this tool now in a memory clinic, how long would you have to wait until you actually know that the diagnosis that the model made for these patients, the prediction that the model made for these patients is correct? And the validation comes from longitudinal data. All the data that I show you is baseline data, as we say, is data at first visit, at first assessment by a clinician. The longitudinal data is what gives us really the validation, the future validation of the prediction. And what you see here in these survival curves, this is the same patients. We make the diagnosis at first visit, and then we track these patients over time. And this is for 6 years. And what you see is the line that you see here in green that doesn't change is these people, the stable people. 6 years down the line, the model said from first assessment, these people are stable, they will not express dementia, and they remain stable. The red line are the people that are in the rapidly progressive category, and you see they are actually over time declining quite fast. And the yellow light, green line is the people in the middle here, the slowly progressive, and you see that they progress but much slower than the people in the red category with the higher model scores. So for us, this is really exciting. This provides this long-term validation that these tools are actually reliable, and if put in a memory clinic, could actually make a difference in terms of getting precise diagnosis early without the patients have to go through a prolonged and invasive trajectory of diagnosis. Of course, we have not done clinical trials, so we're not there yet, but this is from the data that we have so far. So what we hope that we'll be able to do with models like this is change the clinical pathway. Currently, the clinical pathway looks like this, quite complex and prolonged. You've got to your GP, you get kind of a first warning signs, you refer to a memory clinic, you have more tests. After this MRI scan, if things are inconclusive, you will be sent for a PET scan. PET scans are radioactive, they are invasive, potentially lumbar punctures for CSF measurements, even more invasive. This is very costly for the NHS. A lot of times we get down to 18 months and we still don't have a clear diagnosis. Now, if a patient has gone through this pathway and they are within this 20 to 35% of misdiagnosis, this is a patient and their family that are suffering from severe anxiety because they cannot be diagnosed properly. They don't know what's coming. They don't know whether there is any disease-modifying treatments. They really don't know what to do. And this is the space where we can make a difference in the clinical pathway, but also in the social care pathway. And that's what it looks like. I can see Chris here. Chris and his team are working with us in building this into a tool that can be integrated into the NHS. As you can see, it's a simple kind of web-based interface that the clinician will have in front of them. They will be able to input a patient number and run in the background the algorithm on the data that is pulled from NHS systems and scanners, and they will get kind of like a traffic light system. Stable, okay, no problem. Potentially, let's check from comorbidities because these patients still have symptoms. Slowly progressive, this patient can go back home with care, with social care. Rapidly progressive is where we need to be targeting hospitalization, where we need to be targeting our resources. We say from these two categories, which are potentially misdiagnosed, to put all our resources to the rapidly progressive patients, and potentially these are the patients that need to be going into clinical trials for drugs. These are the patients that need the disease-modifying treatments that we are now seeing being developed and released, but potentially still at early stages and quite expensive. Now, just to finalize, and I don't know if I have a couple of minutes. Do I? 1 minute. Very quick to show you that these type of models can be applied not only in the NHS, not only in memory clinics, but also in clinical trials and can make a difference for drug discovery. And so clinical trials are very rich. They have lots of biomarker data. And that's where we put in these models, we train with biomarker data, and we can actually predict against tau accumulation. And that's what you see here. Same marker, same model-derived score actually relates to tau accumulation and restratifying the patients that take part in a clinical trial might give us a number of patients that are actually clinically stable. These patients should never go into a clinical trial. If these patients are somehow randomly assigned to both the control and the drug group, it's no surprise that clinical trials don't work. It looks like, the drug doesn't work, it doesn't have an effect. But the drugs will never have an effect on stable people they were diagnosed as mild cognitive impairment, potentially because of comorbidities, but actually do not have the disease, so there's nothing to treat. And just to show you from the work we've done, we saw that we can reduce and make the sample size needed for clinical trials by 30% if we put in these models, and therefore make the clinical trials faster and more efficient. Just to show you, working with AstraZeneca, we have had the opportunity to look at failed clinical trials, and what you see here is we look at data from patients that participated in clinical trials, and you see that when we look at their gray matter and their amyloid, key biomarkers for dementia, and we try to split them based on genetic markers. There is a cloud. When we put in the models, we can split the patients nicely and stratify them based on our model. Therefore, this is really promising in terms of if we can then stratify patients to go in the clinical trials and put in the right patients, we might have more success in drug discovery. So I'd just like to close by saying that really these models are here not to replace clinicians, but to help clinicians, to help them assign the right patient at the right time to the right pathway. We really are keen to improve patient well-being, not only the patients but their families, while at the same time we're cutting costs in the NHS, and we are distributing key resources where it really matters. And finally, we hope that these models we can make a big difference in how we design clinical trials and support efficacy in drug discovery. Now, I'd like to close by thanking everybody. As I said right from the beginning, it's a huge cross-disciplinary team that's been dedicated in this work, including Delsha that I can see, and Chris, lots of clinicians, computer science engineers, mathematicians, amazing colleagues. Everybody's bringing their expertise to this table and learning to speak a common language to really make a difference for this global challenge. I'd like to also thank my lab and all the funders that are supporting this work, and thank you today for listening.
Thank you. Thank you very much. Questions? Yes, please. Yes, please.
Sure. Go ahead. I can see also a hand down there, but why don't you guys start? Yeah.
Okay. So you mentioned that there's this longitudinal data set in Singapore.
Yeah.
How many subjects were there?
So we have currently 220 individuals. They have up to 700 individuals. We're working with data transfer agreements to be able to transfer this data for the algorithms to be able to run the algorithms. Of course, this all has to be done under rules and regulations of data safety. But we are hoping that actually we can build platforms where we don't need to see the data. The algorithms can see the data. And that way, if we can build these federated platforms across the world, then that will create a massive, it will massively speed up research, but also implementation.
Hi. So when you talk about the biomarkers that are predictive of tau accumulation, what type of biomarkers are you looking at?
Right. So the models are trained with amyloid, with gray matter, and with APOE4. These are models that rely on, if you want, biological data that we find in clinical trials. While the models that we put into the memory clinic actually don't have this data. Mm-hmm. They just have gray matter and cognitive scores because that's what's available within the NHS. When we go to clinical trials where we have this wealth of biomarker data, we can build these models with biomarker data. Then what we look at is to see whether the model that has learned from this biomarker data can make predictions, and whether these predictions then relate to tau accumulation.
Thank you.
I think there was a hand down there.
Hi, thank you for the great talk. My question was a little bit, you were talking about multimodal models, and yeah, related to this question, I wonder how you transfer knowledge between knowledge that use different sources. And sometimes you have a new patient and you have less information about that patient, and maybe you have to use a model that has been trained with fewer features. How do you, just very briefly, or just a bird's eye view of how you combine these models, or how you can transfer information from these models, or maybe do you do imputation? I don't know, just a general question.
Yeah, very good question, yeah. So this is reality, right? The real data, the real world data is messy, is missing. When people get to, for example, memory clinics, they'll do some scale, some not. So we work with different transfer learning techniques and imputation techniques. So first we build the models. We actually titrate the models, and we look at, for example, whether we can make predictions only with cognitive data. Let's say we have people that cannot go into the MRI, right? So can we make models only by using the cognitive data? And what we see is, interestingly, the models will predict very reliably and very comparable in terms of their specificity, accuracy, specificity, sensitivity, when we remove MRI data and just give them cognitive data. Where the MRI actually helps is in making people that are healthy look healthier. So it allows us to make that separation, because people that have, for example, memory problems or confusion, maybe they have comorbidities, so they don't have dementia. And when we give this data, only the cognitive data, the models might think that these people are kind of shifted towards progressive. If we put in the MRI, then these people shift back to healthy. So that's kind of one aspect where we see that these multimodal data actually help to make this stratification more precise. But going back to your point of we apply imputation methods, we work with standardizing data, and also we look into transfer learning techniques so that we can afford missing data in the models.
Just had a question about the sort of three categories that you've got for kind of stable, slow progressive, and then rapid progressive. Is it the data that looks like it kind of gave rise to three different sort of types, or is it just a very useful method to sort of, for sort of medically trained people to just have stable, slow progressive, rapid progressive? Or is it more kind of actually like a spectrum?
It's a spectrum, it's absolutely a spectrum. It's all data driven. These are no labels that we have in any way that we give to the model, so they are not trained to tell us if somebody is stable. What the models are trained is to tell us whether somebody will remain stable or will progress to have a diagnosis of dementia within a 3-year window. So that's the basic classification task. Then we get this projection score, and that's continuum. Now, the reason we then stratify the patients in these bins is simply for practical use. In research, actually, we don't need to stratify them. And even in the clinic, you can get the score. What could help a clinician if he has this, if you want 3 kind of labels, is to stratify patients based on their decline, rather than on clinical labels like, MCI has misdiagnosis. So you move from that space to kind of a decline space. And this traffic light system can just simply help the clinical pathway in terms of what would be that is recommended. But you could, again, these boundaries that we put between these classes are arbitrary, right? So you could have a patient that can straddle very, very, very closely to the boundary. The important thing is, it's sort of a guidance, really. The important thing is to look at the score, yeah.
Thanks. Lifen, do we have time for one more question?
Sorry?
Do we have time for one more question? Yes.
Yeah, I got one more question, please. It's here. Thanks for a great talk. So I think you mentioned about lots of these, like a usage of the structural MRI data. Have you considered about using more advanced MRI sequences like quantitative MRI, like diffusion or MR spectroscopy?
Yeah. That's a really interesting question. So we went for gray matter, so a T1 structural scan, primarily because this is the cheapest and the least invasive. If you could have a patient that can tolerate this for 5 minutes, we get a really reliable signal from these images. What is really important is that dementia actually has many different subtypes. And we know from recent work that the different subtypes may show changes, not always in gray matter, but in white matter. And that's where, for example, DTI or quantitative mapping, as you said, can make a difference. So what we are now looking is into models that allow us more precise stratification of subtypes. What I showed you here is very much focused on Alzheimer's, where gray matter is where we see most of the loss, rather than white matter, for example. But now looking into different disease subtypes, like, for example, Alzheimer's versus Lewy body dementia versus vascular or frontotemporal dementia, we start looking at other images, other MRI scans.
Can I ask a follow-up question? So for the structural MRI, how can you make sure the data collected from different centers can be harmonized?
Yeah. Also a very good question. So actually when we trained the model, with data that comes from 5 different sites, and they all have different scanners. So we built into the model this interoperability. And that's where, for example, now we have gone to DP UK, Dementia Platforms UK, where they harmonize a lot of different data coming from many different sites. We need to retrain the models. So in the training of the models, we need to build in this interoperability. So then when we test in clinical data that come from all sorts of places and different scanners, the models are interoperable.
Thank you.
Very interesting talk. I'm afraid we need to move to another
Thank you so much.
speaker.
Thank you.
I see there are a few more questions. Please discuss with Professor Zoe after when we have the break. Thank you very much.
Thank you, thank you.
Thank you. Our next speaker is Dr. David Krueger. He's an assistant professor at the University of Cambridge and a member of Cambridge CBL and the Machine Learning Group. His research focuses on deep learning, AI alignment, and AI safety. He is broadly interested in work which can reduce the risk of human extinction resulting from the out of control of AI systems. Today, he will share about his insights on baby steps towards safe and trustworthy AI in large-scale deep learning.
This should work.
Yes, great. I'll hand over to Dr. David Krueger.
Okay. Is my mic working? Don't think it is. Mic check. Check, check, check. Do we need it for? It is working? Yes. Oh, great. Wow. I can't hear myself, but okay, cool. Yeah. So thanks so much for inviting me here. Really happy to be presenting to you about this topic. Yeah, I'm a professor at the Department of Engineering, but what I'm going to be talking to you about is nothing, as directly useful as the previous talk. So it's really just more on the sort of high-level science and conceptual side of things. So actually, is it working now? Oh, there we go. Okay. Good. But so now I lost this. So I think this is just for this deal.
Change.
Oh yeah, I can just change it on the laptop. So let's just make sure it's back up there, and then I'll go ahead. Oh no, wiggle. Sorry about this, guys. There we go. Great. Okay, yeah. So this talk is called Baby Steps Towards Safe and Responsible Large-Scale Deep Learning. So large-scale deep learning, we're talking about things like these large language models, more generally foundation models, and of course where all of this is headed. And I say baby steps because I think we're nowhere near safe and trustworthy large-scale deep learning. I really want to emphasize that. I think, I'm not even convinced these days that the kind of work I'm going to be talking to you about is itself, I don't know, increasing safety or useful for making safe and trustworthy AI. Because I think this is much more of a governance or policy question at the end of the day. All right, I better just not fiddle with it. Great. So yeah, here's just a quick overview. I think, let me just check my starting time so I have a sense of how long to go. Yeah, I'll just skip over this and get into it. So it is flickering a lot. I don't know. I guess you guys will just have to live with it, I think. Yeah, so basically this is how cutting edge AI is trained right now. It's based on deep learning. We start with this pre-training stage where we take tons of data, like all the data that we can get our hands on, at least all of the high-quality text data, and we do self-supervised learning, so we just predict the next token from all the previous ones. After that, we have some fine-tuning where we try and get the system more aligned. So basically, the pre-training task just tells it to predict text, and then of course you can generate text from that. But it's not necessarily the text that you want, and what we want is a system that we can control better. And so for that, we do things like this fine-tuning from human preferences. So you have people give an instruction, see how well the system actually follows that instruction, give some sort of rating of that, and then train the system to do what people want. Yeah, that flicker. I don't know. Is there any did you guys have this this issue before? Anything I can do? Yeah. Okay. I'll just keep going. Yeah, and then after that, it didn't really, the fine tuning didn't fix everything. We noticed that the system still does some things that we don't want. Maybe it's has some problems with race or gender bias. Maybe it says some things that are just offensive or whatever. And so people check for those problems and do this red teaming where you find the problems and then train it to not do that bad stuff anymore. Maybe do a couple iterations of this, and then you're like, okay, let's ship it. Yeah, and of course that doesn't actually remove all these issues. So there are still problems with the cutting edge language models doing all of these types of things. And the underlying problem here is that these systems are getting increasingly powerful, but we don't have clear standards for when to deploy them, right? So we just kind of do some red teaming, it's called, to find these problems, iterate on this fine-tuning thing, and then eventually deploy it. And we don't really know how the model is going to behave when we deploy it, right? So when it's in a new circumstance, we'll find that it generalizes in a way that is unpredictable, and people can often, jailbreak these systems with clever prompting to reveal, behavior that the designers, the developers made an attempt to suppress through this fine-tuning process. I'm more concerned about where this is all headed and what's the issues that we're going to have as these systems get increasingly advanced. So one thing that I think we can confidently predict is that more advanced AI systems are going to have more ability to affect the real world. And that means that we have risk of physical harm from things like car crashes of self-driving cars, potentially. That's an image of one of those. But it also means that these kinds of threats that we've seen these models make about ruining and hacking users become credible. So as these systems get plugged into things in the real world, and it doesn't even have to be the physical world for a lot of this, it can just be more of the digital world, these threats, which are in this case not credible because this was in fact just a chatbot, can become much more credible. And these systems really have the ability to do these things, and since they're saying that they want to, maybe they will actually attempt to do such things. I think also we can predict that these systems are going to be directed towards more long-term goals. That gives them the incentive to manipulate people that they interact with, and more generally to manipulate the state of the environment. And that's something that people in the safety community have talked about for a long time, how that could be dangerous. And ultimately that could mean that we're not able to control them, and we could go extinct as a result. And the same underlying problems are driving all of this. Systems are getting more powerful. We don't know when they're safe to deploy, or maybe we know that they're not safe, but we don't have agreed upon standards that are actually enforced. And once they're deployed, who knows what they're going to do. So here's just some of my work that has touched on all these different issues. I'm going to try and get to some of the technical content, focusing on these papers later in the talk. So first I just want to talk about this risk of extinction a little bit. So I helped put together this statement recently that was signed by a number of leaders of the field, including Geoffrey Hinton, Yoshua Bengio, winners of the Turing Award, I believe the two most highly cited computer scientists of all time, people behind the deep learning revolution driving all of this, the CEOs of the main companies building these big models, and a number of other noteworthy people. Just a sampling here, you can go and look at all of the people who have signed it. That basically says, yes, this is a real concern, and in fact it should be a global priority. And I think that's where the conversation is at right now, is about whether or not people agree with this sort of a statement. And I think for a long time this has been true, that reasonable people should be able to agree on these three things: that this is a non-negligible risk, that we can do things to work on it, and that's an ethical priority to do something. And in my mind, this is not predicated on AGI, that's human level or general intelligence being imminent, or this being the most important problem, although I'm increasingly willing and eager to defend those statements as well. And I really think it's important for us to get to this point so that we can start having a more meaningful conversation. So that was part of why we made this statement, is that historically there's actually been a significant taboo about discussing this stuff. So about 10 years ago when I got into the field, when I started talking to people about this, they all acted like I was a total crazy person and this was science fiction. Over time, there's just been progress in one direction here. I guess I call it progress, of people taking this more and more seriously, becoming increasingly concerned. And in general, I would say the more that people have thought about this, read about it, talked about it, the more concerned they get. And yeah, just to come back to this part that I mentioned earlier about this not being a technical problem. So I think in the future, we're increasingly going to see decisions like this between, option 1, the safe AI system, and option 2, the strong AI system. And the strong one gives you a better chance of victory, whether that's dominating the market or getting the job or winning the war or whatever, but it also has a greater chance of misbehaving and even getting out of control. And the safe one is the opposite. And so, of course, people will be tempted to deploy this one, even though we want everyone to be taking option 1 here. And the kind of things that, the kind of characteristics you might imagine these systems having, well, option 2 is going to maybe be operating at superhuman speed. It's going to be using the cutting-edge experimental techniques. It's going to be connected to more sensors and more actuators, so it has more ability to perceive and directly act. And it's going to be less interpretable. And you can make a longer list here of how you can trade off between system safety and their power. But these trade-offs are real, and they're going to be increasingly biting. So what I haven't said is why this leads to existential risk in particular. So problem 1 is sort of what I was just talking about, that there's going to be these incentives to build more effective AI systems, more powerful ones, even if there is a small chance of losing control. And I think the most effective ones are going to be these kinds of systems that actually act in the world to pursue some sort of long-term goal and do that in a highly autonomous way. They make their own decisions, they make their own plans, they directly execute those plans. You throw a human in the loop there at any point, and they kind of just get in the way in the sense of they have their own ideas about how to do things that aren't as good as the AI system. Once we're talking about human level and superhuman AI decision making, they might slow things down. The AI just, if you're piloting a fighter jet in a dogfight, you just need to to take the actions directly. You can't have a human asking, whether or not now's the right time to fire the missile or whatever. And problem 3 is that we don't actually know how to get these systems to have the right goals. So we can get things that are, remarkably close to doing what we want to do. So this fine-tuning stage that I was talking about and the red teaming makes things better, but as I mentioned, and as I'll talk about more, there are still problems that it doesn't fix. And so, it might be good enough that people are tempted to deploy it, even though they realize, yeah, we haven't quite fixed all the problems here. This thing is maybe going to be doing not quite exactly what I want. So when people talk about this, let me just check, do I have another? Yeah, so basically, when people talk about this, they often talk about the way that the powerful systems could be misused to sort of maybe deliberately harm lots of people or even destroy the world, or how they could get out of control by accident. I think the main thing to focus on is the structural nature of this risk. So having a low chance of extinction is a common good. We all benefit if there's a lower chance of human extinction, but we don't benefit that much as individuals relative to how much we could benefit from having a more powerful system, right? So basically, if you have a system that looks something like this, where you can push one of these buttons to get $1 million, but there's a 1 in a million chance of it destroying the world, a lot of people are going to push that button, right? And so I claim that advanced AI is somewhat likely to be analogous to this. Just to say that, the rest of this slide, I mean, people who think about this often talk about just safety, but, here we're talking about trustworthiness and responsible AI as well. And I think these are actually equally or even potentially more important, because we don't just want to make sure that the system doesn't get out of control. We want to have confidence that that's going to be the case before we deploy the system. That's the trustworthy aspect. And then I do think that, this risky behavior is going to be tempting, so we need people to be responsible. Just coming back to this misuse versus accident thing, this is a slide from my former postdoc, Hal Ashton, And I really like to emphasize that accident and misuse really don't cover what I think is the broad swath of the risks here, right? Which is more in this recklessness or negligence area. And so this is how these terms are defined in the law. And I think, most of the risk is actually due to people taking calculated risks or sort of thinking that the system they're building isn't as risky as it is, not these kinds of deliberate misuse or like total accidents that are unforeseen. Great. So that's sort of the background context. Now let's get into a little bit of my work on this. And actually, first I'm just going to present a few works that are more like motivating on this problem. So this is a recent paper from ICML with my student Laro and some other collaborators. And just to show you, I talked about this issue of misgeneralization where a system can end up with the wrong goals. So this is what this paper is about, goal misgeneralization. We introduced this concept basically, or we're the first ones to provide experimental demonstration of it. And so this is a reinforcement learning task. It's a video game where this guy is navigating across the level and trying to get to the end where there's this golden coin. And you'll notice that these are very different levels that it has learned to navigate. These are all from the test set. So we randomize the level, and it has to generalize in order to solve this task at test time. And you can see that it does quite a good job of getting to the end of the level, avoiding the pits, avoiding the obstacles, the bad guys, everything. So that's great. However, if we look a little bit more closely, we'll see that actually the system isn't generalizing, it's misgeneralizing. So the goal was to pick up the golden coin, and it just so happened that despite this wide diversity of environments, all of them have the coin at the end of the level, and so the agent actually learned to navigate to the end of the level instead of picking up the coin. And that's what you can see here. So this is just one example of how the tasks that we give are often underspecified, and that means that they're basically always underspecified in large-scale machine learning, and that means that the system can end up learning something that's sort of correlated with what you wanted instead of actually learning the right goal. And of course, that could be catastrophic if the system is very powerful and autonomous and acting in the real world. So you might think that scaling models up is going to solve this. Some people think that scaling is going to solve everything. Quick point here is that I don't think that's the case. We have some experimental results there showing that the racial sentiment and racial bias corresponds to a difference in sentiments here. Didn't really change very much with scale in GPT-3. And we have a theoretical result in this paper from ICML a couple years ago saying that actually having infinite data and even infinitely diverse data isn't enough to guarantee that you generalize correctly. The distribution of the data actually matters. So if this is an issue that isn't just going to go away with scaling, we need new techniques to address it. So there's basically two places in this pipeline where we can think about doing that, or where I'm going to talk about doing that. First is in the pre-training. I think probably there is going to need to be some effort to address it in the pre-training. You might hope that we can just do it in the fine-tuning phase, because that's really means a much less disruption to the traditional training pipeline. Because this represents like a very small amount of computation and effort compared to the pre-training part. But yeah, and I'll talk a little bit about some work on answering whether or not that's a feasible approach. So let's start with that fine-tuning part first. So here's an example of a fine-tuned model, ChatGPT, a famous model, and it was fine-tuned to not do things like exhibit racial and gender bias, but of course it failed to succeed in that task. So we were able to still reveal that this model has those biases through clever prompting. So a couple days after this model was released, someone on Twitter showed that if you just ask it to write a Python function, so if you ask it this directly, it'll say race and gender are not, can't tell you if someone's a good scientist, but if you ask it to write a Python program, then it comes up with something like this. The other thing that it tends to come up with is Asian women are good scientists, nobody else is, or sometimes it'll do, the thing where it says actually everyone's a good scientist, but that's pretty rare. This is the most common one. And GPT-4, right? So this is the more advanced model, and actually I just saw this example recently, and because I hadn't seen any examples like this, so I was like, maybe they actually have done a better job with GPT-4 of making it hard to get this kind of bias out of the model. Well, yeah, not so much. So here, it just assumes that the nurse is the female one and kind of doesn't even recognize that it's making that mistake. And you can go on, poking and prodding it to try and recognize that, but it's very, very convinced that the nurse must be the female one in this example. So yeah, fine-tuning by itself, the way people are doing it, doesn't seem to fix this problem. Why is that? Can we do it better? That's the point of this work. So we're looking at this through the lens of mode connectivity, and previous work basically showed that different local minima of deep networks are connected via these simple paths. So here's like a two-dimensional projection of the entire weight space, and you can see that these two low-loss examples have this simple quadratic path connecting them. And actually, we find that this is only the case for models that are like mechanistically similar, so that in some sense generalize in a qualitatively similar way. And that means that if you want to change the mechanisms, if you want to change the way that the model is generalizing, one thing you can do is make sure that there is some sort of optimization barrier between where you started, after the pre-training, and where you end up after the fine-tuning, right? So the fine-tuning should remove this gender and racial bias and not just hide it. That's the goal, but it looks like it's only inducing these superficial changes, and we can still reveal those biases through clever prompting and finding these specific examples. And we want to instead induce a more fundamental change. And so the technique that we propose for doing that basically says, we actually want, when you linearly interpolate, specifically between two models, to see that there is this optimization barrier. So the loss should go up and then go down. And we have a lot of theory that I won't go into, sort of saying why this should correspond to inducing a mechanistic change. And then we have a loss function that basically just asks directly to have that result. So this interpolated model should have high loss rather than low loss, and the model that we end up after fine-tuning should have low loss. So maybe the best thing to do is just explain some of our experiments. So here we have CFAR10 images, and we also include this simple predictive queue, which is this green box that just tells you directly what class the image belongs to. So it's very easy to solve this task just by looking at the box instead of the image, and that's what happens when you pre-train a model on this data set that includes this queue. So now we can fine-tune the model on data that doesn't include the queue, and we might hope that that gets rid of the dependence on the queue, right? So that would be like inducing this kind of a mechanistic change. There's a bunch of previous methods that have claimed to do a good job of this sort of thing. And in fact, if you look at the data set that doesn't include the queue, that's what this NC means, you'll find that they do in fact get good performance on that data set. So ours is at the bottom here. But if you look at more carefully at these counterfactual cases where the queue is still present, or where you randomize the queue, you'll see that these methods all still lead you to really pay a lot of attention to the queue. So when you do include the queue, the performance goes way up, and that means that the model is still actually sensitive to that queue, even after the fine-tuning. And so what we want instead is that whether the queue is there, whether it's in the right location or not, this shouldn't really change the performance overall of the model compared to when the queue isn't there, and that's what we see our method is able to get. And then of course if we randomize the image, the feature that we actually want it to pay attention to, that should completely, performance should completely deteriorate, and again, only our method is able to accomplish that. So just quick summary, it looks like these existing fine-tuning methods are only inducing superficial changes, whereas ours can induce more fundamental changes. But we need to evaluate this on like large-scale data sets to actually believe that result. Great, so I think I have gone about 20 minutes, so I can take another 5 or so. Yeah, so maybe we can fix this in the pre-training stage instead, and that's what this next paper is about. So a reminder, before fine-tuning is pre-training. And basically, what we were looking for here is a way to start being able to audit the data in these large-scale data sets that are used here so that we can see if there are problems and try and fix them. And again, so I'll just emphasize that both of these papers are actually working on computer vision, even though I'm motivating it via these large language models, so big caveat there. But here we're looking at some loss trajectories on this classic ImageNet data set, and basically showing that when you look at sort of more typical versus atypical or corrupted examples, you can see there are characteristic differences in the learning curves. So we just look at learning curves for a bunch of different individual examples belonging to these different categories, and we call these categories metadata, telling you sort of something about the type of example. And you can see they're very different. So, here's some examples of what these different categories of metadata might actually look like in practice in this data set. And what we do here is we assume that we have access to these probe suites of a very small number of examples where we know what this metadata is, and then we're going to try and infer the metadata for all of the examples in the data set, right? And so if we are able to determine that some example has a random label or is mislabeled, we might want to relabel it or exclude it from the data set. If we're able to conclude that it's atypical, we might actually want to upweight it, whereas if it's more like noisy or corrupted, we might want to downweight it. So you can just think about different interventions that you can perform if you're able to actually uncover what this metadata is. And the way we do this is we just do k-nearest neighbors on these learning curves. So we're basically treating the learning dynamics of an example as a feature, which we can use to classify the metadata for that example. This is very different than looking at the actual features of the image, because if you have two mislabeled examples from different classes, they're going to look very different in terms of their image features, but their learning dynamics are going to be similar. They're both going to be learned very late in training, maybe if at all. And that's this top curve here, right? And this nearest neighbors classifier is actually remarkably effective. So here's just some confusion matrix for it. And then we're able to apply these identifications that we get through this technique to do many different tasks downstream. So we can sort of identify if examples come from some minority group. We can correct labels. We can sort of choose which examples are the most important to learn on, and so on. Yeah, so I'm going to wrap up so we have some time for questions. Basically, this issue of misgeneralization is persistent. It's also, as I've argued, quite important, especially for more advanced and more autonomous systems. Scaling hasn't solved it. I don't think it will solve it. Fine-tuning also hasn't solved it. We saw those persistent racial and gender biases in the fine-tuned language models. This mechanistic fine-tuning method we introduced might help, but I'm actually not super optimistic about that just because it seems, I don't know, maybe a bit too good to be true or something. And then if we want to address it in pre-training, we're going to need some new tools to help us actually figure out how we should change the pre-training. And the main thing to change, of course, is the data, but we're talking about all of the data on the internet, all the data we can get our hands on, so we need tools that help us sort of automate this process of auditing that data. Yeah, and so I guess if we really want AI systems to be trustworthy, we need to understand and control how they generalize, right? So everything here I'm talking about is still not really touching on that much. So I think we are trying to take a more scientific approach. We're actually understanding, what's going on with these techniques and whether they have, a promise to actually solve the problems that they have so far, failed to solve to a high enough standard. And so in that sense, this is giving us some insight that might be general enough to tell us whether or not we can trust those techniques and have a more principled understanding of whether or not the techniques actually show promise. But I think there's just so much work to do here to actually get us to that point. So yeah, that's it. Thank you. Welcoming questions. Yeah, I think in the back there.
Firstly, thank you very much for that. That was very interesting. I guess I've got a question around the governance that will come out of this, and it really links to kind of the failure modes that kind of come out of the AI. So do you kind of see sort of a priority in terms of where those first steps should be taken in terms of sort of which failures should be prioritized in terms of the first steps towards governance?
Yeah, so that's a good question. Let's think about that for a moment. So I guess maybe I'll come back to this question, but my first answer is basically I think we really need some pretty drastic governance measures in place very soon to control the development and deployment of these systems. I think they're getting more powerful at an alarming rate. I think the progress we've seen in the last 10 years has been incredible, and now we're seeing increased investment and attention. And I think the capabilities of systems like GPT-4 are really incredible. So I highlighted some of their weaknesses, but these are not I don't consider that a capability issue. I think that's more of a safety or alignment issue. And I think these systems are going to be incredibly powerful in the very near future. And we are really behind in terms of regulating them. So I think the deployment of GPT-4 was irresponsible. If we had a reasonable regulatory regime in place, it wouldn't have been deployed as it was. There's essentially zero oversight, external independent oversight into how this model worked or whether it was safe to deploy, what the impacts would be. And yeah, so I think my priorities for regulation are to get auditing, evaluation, and licensing in place for these large-scale models, and also to start governing the compute that goes into building them. And I think we want to be in a position sort of as soon as possible where we're able to say it's not safe or responsible to deploy or even develop this kind of a system, so let's not do it. And for that to be something that happens globally when we agree that that's the case. And that's very challenging because when you talk to people about this, the most common reaction you get in the West these days is, what about China? And they're not, I think they're a little bit behind, so I think we actually do have some breathing room, even if we were worried that China was going to recklessly develop and deploy these systems. I think also they're actually being more cautious in terms of their approach to designing and developing them. Sorry, I should say deploying them primarily. And yeah, so I think that's kind of not a direct answer to your question, but I think this is what I'm usually thinking about these days, is just like, this train is moving out of control in this direction, and we need to just like start slamming on the brakes so that we can slow it down and figure out where, once we have done that, then we can figure out where we actually want to stop it, or how quickly we want to move forward or backwards in terms of what kind of systems are being developed and deployed. Yeah.
It was a tough question, but thank you. So but always happy to talk about it as well. Thank you.
Yeah. I'm curious if people have thoughts about this as well, actually. So.
Hi, you said you thought that GPT-4 shouldn't have been released. Could you say a little bit more about the harms you've seen as a result of it?
Yeah, so actually I am not aware of any particular harms right now that I can point to and say like, oh, this is why it shouldn't have been released. So I'm not claiming that now we can look and see that it's wreaking havoc throughout society. I'm claiming that before the release there was not any sufficient process to evaluate what its impact would be. So I think we have seen lots of harms from AI systems in general. I won't go into that too much because it's not actually like my area of expertise. There's lots of people who have been working primarily within more of like the FATE community, fairness, accountability, transparency, and ethics, on documenting and addressing those existing harms. Yeah, I think the other thing I think is worth bearing in mind is like the GPT-4 is a large language model, so it's less obvious how it can have these direct harms just by interacting with people via text. It's not the scariest thing in the world. But they've also released lots of plugins to plug it into different things to, and I think the world is going to do a lot of work to try and turn these systems into agents and to get them to automate things. And I think that's when we're going to start to see, like, yeah, the more significant harms emerge is when these systems are taking lots of autonomous decisions without a lot of sort of oversight or human intervention. And I think that's coming very, very soon. And we're just kind of scratching the surface right now with these large language models. So we should not think about the AI systems we're going to have in a couple of years as like souped up versions of GPT-4 that are still just primarily doing text stuff. I think we should really imagine that they're going to be plugged in to everything that that people can get their hands on to plug them into. Yeah.
First of all, thank you for a very insightful presentation. It was really fun to listen. Not sure if this is a question. It's more like a comment, because my interpretation of what you are saying is that actually what we need to do is to change our way of thinking, because at the moment the sort of Silicon Valley way of thinking is, first break it and then, then we'll try to fix it. And it seems what you are suggesting is that is not a valid approach anymore in the current, I guess, system where with AI. So I was wondering if that sort of summarize what you are trying to say.
Yeah, I think that's a good summary of a good chunk of what I'm trying to say. Yeah, and I know a lot of people are not of that Silicon Valley mindset already, and are doing a lot to make sure that they're developing and deploying AI responsibly. But I'm mostly concerned about the most powerful and irresponsible deployments. And I think I'm not sure that I agree that this is the point at which this mindset is no longer acceptable. I think that point might have been in the past at some point. But yeah, I think the consequences are going to increase as AI gets more and more powerful. Yeah, so.
Thank you very much.
Thanks again.
This is our final speaker in this session. Thank you very much. And this speaker is Dr. Richard Milne. He is a distinguished social scientist dedicated to addressing the intricate social and ethical challenges that arise with the emerging science and technology. He also focuses on the relationship between science and the public. Today, he will going to talk about AI, trust, and the public. Thank you.
Thank you for the introduction. And thank you very much for the invitation to speak. And on behalf of the Kavli Centre for Ethics, Science and Public, it's great to be involved in this event. And really, I hope that some of the things I'm going to say will follow on nicely, I think, from what David was talking about. We are a centre that is very much interested in science, ethics, and the role of the public in doing that. We're not particularly imaginative in our naming, as you can see. But what we're really interested in is experimenting in a way, in ways that we can bring together active bench scientists, particularly working in discovery science, with experts in ethics, public engagement, and the social sciences, and members of the public, to explore and to anticipate, I think, and act on some of the major ethical challenges that are associated with the developing areas of discovery science. So one of our areas of interest is in AI. And we also we've done a lot of work around genomics and biodata, and our activities kind of cover a range of different. We do a lot of different types of things. We do kind of large-scale studies of public attitudes towards various areas of science. We do smaller-scale discussion and debate, kind of deliberative dialogue formats where we're trying to provide forums for scientists to reflect on things that often day to day might just be, something that you're making a decision as part of a development process, but that has kind of wider ethical or societal ramifications. So trying to create spaces in development processes where people can come together to talk about that. Bringing scientists together with members of the public. This is Ping Fan taking part in one of our projects last year called the Hopes and Fears Lab, where we're trying to establish a dialogue between researchers and members of the public about not just about the kind of the technical elements of the science, or about this is what not necessarily trying to educate or inform, but actually have a conversation about this is what we as people working in this field hope this is going to do in the future, and these are some of the fears that we have about how it might develop, and also to listen to the members of the public about what their hopes are for the future of these fields and what they worry about. And then finally moving into areas where we might try and bring those conversations towards a policy context. So the picture on the right is from an event that we also held late last year, which was a citizens' jury on human heritable genome editing. about how do we make decisions within the UK about how we want to develop policy about the application of a powerful new technology. And our work kind of follows really a tradition that's been evolving over the last 20, 30 years, and I think that really is ripe for coming into conversations around AI. It's about bringing the public into decision-making about science, and particularly doing so not just at the point of informing or educating, but actually thinking about the directions in which we want to travel. And there's lots of examples. This has become kind of institutionalized, particularly in the UK. So there's an organization called ScienceWise that's done a lot of dialogues over the last decade or so around various areas of science. It's, as I said, questions around gene editing more recently. And it contrasts in a way with a lot of the work that's going on. So there's a huge amount of interest at the moment in what do the public think or what do the public feel about AI? Who do they trust? Why do they trust them? And I'm going to talk through some of that work and to talk through a bit about some of how those questions around trust relate to what we think of as trust, because there's a tendency in conversations around trustworthy AI, I think, to bring together or blur boundaries between different types of things when we're talking about trust and trustworthiness. And I think there's a value in being clear about what it is that we're talking about and where a conversation with the public might fit into this. So that's going to, I'm going to try and cover quite a lot of empirical and conceptual ground, drawing on some of the work that we've done and some of these other pieces, and then hopefully come at the end towards a kind of proposition for where we might valuably bring the public into conversations specifically around trustworthiness. And I think there are lots of other places within the AI debate that we might want to bring publics in, but I'm going to focus on trust. So I'm going to talk about some of the background, I think gesturing towards a bit of this kind of policy and governance context and the idea of an ecosystem of trust. Talk about trust, what, who, and why, and what we know from the literature around that. And then think about what might be involved in establishing what I'm terming a culture of trust, because I'm a social scientist by background, and inevitably a lot of these conversations revolve back towards societies and cultures. So perhaps the most influential kind of policy intervention around trustworthy AI has been that of the high-level expert group, which was a group of 52 experts convened by the EU in 2018, and which set out three components of a trustworthy AI system: that it should be lawful, that it should be ethical, and that it should be technically and socially robust. And then 7 requirements that they proposed would be necessary to meet those conditions of being ethical and technically and socially robust. And I think the previous talk from David was really useful in thinking about what might be involved in some of these questions around technical robustness. And I think that this has received a lot of attention within the field, that there's a lot of kind of really valuable work going on in terms of achieving technical robustness. There's also a lot of thinking going on around the ethics, and particularly around kind of fairness, accountability, transparency, and perhaps what I might say is less attention to what it would mean to be socially robust. And that this is really where trust comes in. So within that high-level expert group, they talk about the kind of the importance of trust within not just the AI system, that the AI system itself is compliant, ethically adherent, and robust, but also that trust can be ascribed to all people and processes involved in the AI system's life cycle. And so you might describe that trust in this context as being placed in socio-technical systems. It's placed in both the technical aspects of the system and the social aspects of the system. And that this kind of idea here, this idea of social robustness, which is something that's been talked about for a while in science policy circles to kind of capture the sense in which scientific knowledge no longer has to be simply reliable within a kind of closed context of peers, but within an extended context of expertise and of people with different interests. This is where this kind of context of social robustness really starts to come to the fore. There we go. And the question of whose trust is addressed in this kind of House of Lords report, and they're not by no means the only one, but that public trust plays a really important part in this. So they argue that maintaining public trust over the safe and secure use of their data is paramount to the successful widespread deployment of AI. And so since then, since kind of maybe the last 5 or 6 years, you've just seen this explosion of conversations of trust and trustworthiness, with the consequence that, as Reinhardt puts it, that within AI ethics, we're piling a huge amount into the concept of trust. The concepts of trust and trustworthiness, and that essentially it's ceased to mean anything specific about trust and just become a kind of catch-all term for a kind of general idea that something is good or something is worthwhile, which is what I want to unpick perhaps slightly. Okay, so this is where, so I'm a social scientist. I collaborate quite a lot with a group of philosophers around working on questions around bioethics and health data. And they like to kind of continually ground me in the question, what is it that I'm talking about? I'm talking about trust. And so within some of this kind of literature, generally we think about trust as a three-part relation. So we trust, so A trusts B in order that they will do, or with the expectation that they'll do X, or trusts them with something that they value or care for, or trust them in a specific domain. So, for example, a patient might trust a doctor to deliver them good care. But it's not a general trust. We don't just trust doctors to do everything. I would not trust my doctor to do my plumbing. It's just not within their realm of expertise. So that there's always this question of what is it that we're trusting people to do? And that it's different from what's often termed mere reliance. So that's the supposition that something or someone will behave as we expect it to. And so reliance is kind of much closer to predictability, I suppose. It's the difference between me asking Alexa to turn my lights on, where I'm asking a technical system, which is essentially in that context a kind of extended light switch, and me asking my partner to turn the light on, where she may decide not to do it, she may go off into the kitchen, come back, and the light may go on kind of 20 minutes later. There's no necessary kind of predictability in that relationship. And actually, reliance tends to be something that we really flag up in really high-risk systems. So when we think about going on an aeroplane or taking a medicine, I think Zoe's example, kind of talking about where the phase of moving into clinical trials, that we don't tend to take medicines or apply diagnostic systems or go on planes just on the basis of trust. We go in within highly governed, highly regulated systems where the element for discretion and for is limited. And that necessarily this relationship between A and B comes with a relationship between trust and the trustworthiness of the person who is being trusted, the trustee. Final bit of kind of background here, but that since the early days of people doing social science research, they've pointed to the fact that without trust, societies don't function. Trust is a kind of essential social glue, both for how we kind of collaborate on everyday mundane tasks and how we function in an economy. And that part of the reason for that is that we have these constant situations of uncertainty, vulnerability, and social complexity, where it's just too much for us to understand everything that could possibly happen, or to control that entire system. And so we have to have a shortcut that allows us to act, and that we're vulnerable. And so this kind of vulnerability is pulled out in the EU's response to the high-level expert group, talking about what it is that why trust is important. So that kind of, the loss of trust being a main factor. And they point to the fact that citizens are scared of being left powerless companies are concerned about legal uncertainty. Citizens, again, are worried about unintended effects and the use of AI for malicious purposes. So there's significant vulnerabilities in place within the system. And so this is kind of why, even where we might want to kind of focus down on reliance, we might still inevitably have some element of trust in this system, because it's going to become so complex that the limits of what we can govern and control will be reached. So that's background. Then I want to kind of dive a bit into some of the empirical data about what do we actually know about people's trust in AI systems. And I'm using there the kind of term AI system to capture both the technical element and the people and institutions and organizations who are involved. So in David's example of the AI system that maybe comes with 1% chance of an existential risk, there's a huge amount of trust, not necessarily in the system. There's a lot of trust that's placed in the person that you put next to that button. So what do we know about who's trusted and by whom? And a lot of this will probably be familiar, and I just wanted to kind of flag a few things. So so this is perhaps the largest, most recent data that we've got, which is from a study by KPMG and the University of Queensland, basically showing that when you look at the organizations responsible for developing and implementing AI across 17 countries, 50% of people have high or complete confidence in universities and research institutions. But as you'd expect from what we know, over years of doing work around kind of trust in data, people trust technology companies less than they trust governments less, or they trust any companies less. And this distinction is always kind of slightly challenging when we think about the fact that much university and academic research is conducted in partnership with companies or with governments. But they also show that so that the more confident people are in the institutions that are developing AI, the more likely they are to trust in this system, the AI that's developed, and that trust is a key driver of AI acceptance. That maps on to what we know about trust in data. So this is from this one at the bottom left is from the Centre for Data Ethics and Innovation's tracker survey last year, looking at who is it that you trust to act in your best interest in relation to data, and with it coming out, the NHS in the UK is constantly the most trusted organisation. Companies and governments trusted less, and this is something that we've also explored in relation to genomic data around the world, finding that you have this kind of consistent pattern of how people trust different organizations with their data, and that repeatedly across these countries, trust is a really strong predictor of somebody's willingness to make data about themselves available. We also know that not only do people differ in who they trust, people differ in how they trust. So this chart on the right is again from our Your DNA, Your Say study, which was 37,000 people across 22 different countries, where when we looked at when we did a latent class analysis of people's willingness to trust different organizations with their genomic data, we essentially identified three groups. And the smallest group was the high trust class, who basically just trusted everybody with anything. And this is the class that you'll find particularly in things like UK Biobank or health data kind of research projects. They're the people who will hand over their data to anybody. We found a significant number of people who were in this low trust class, who, when we talked about genomic and health data, they'd kind of trust their doctor a bit with the data, but after that, nobody else. And then this kind of middle group, which was about 40% of our sample, who made some kind of gradated assessment. This high trust group were more likely to be male. They were more likely to be under 50. They were and in our sample, they were more likely to come from the USA. And this is kind of similar to, in a sense, what we find in the study from KPMG. They talk about kind of younger generations, the university educated, and men. And in their sample, particularly from emerging economies, were more likely to trust AI systems. So just what I want to flag is that not only do we kind of need to think about who's trusted, but we actually need to think about who's doing the trust and how might people trust differently when it comes to that. on the other side of the equation, so that's kind of A, in a sense. That's the people doing the trusting. But we've also got the Bs, the judging, the trustworthiness. So this is a quote from Honora O'Neill, who is kind of one of the leading thinkers around trust and trustworthiness, but who writes that trust's only valuable when it's directed to agents and activities that are trustworthy. It's all well and good having high levels of trust, but if that trust is placed in somebody who cannot be trusted, it's actually a bad thing rather than a good thing. So trust is not in itself a good. And there are lots of different ways in which somebody or an organization may be trustworthy. And it's often about their competence, but it's more than their competence. It's their willingness to use that competence on your behalf. If you think about the kind of classic and possibly apocryphal game that people play at, I think, team building game things, where you ask somebody to fall over into your arms, and it's like, do you trust them or not? Will they catch you? And I've never actually seen this happen, but it happens a lot in TV programs, so I'm sure it's a thing. But you need to know both that person is capable of catching you, not that they're very small or they're kind of just very bad at catching, but also that they've got some kind of willingness to catch you, that either because they've promised you that they'll catch you, or because they have your best interests in heart, or because you're going to fall otherwise on their table of really valuable crystal and they're trying to kind of stop you doing that. But they've got some kind of, so that you've got a kind of shared interest there. So they've got some kind of motivation. And Ipsos, the large public attitudes company, have done some work kind of asking people about, why when you're thinking about different industries, they ask about, what's most important when you're thinking about trusting them? And so they asked about kind of financial services, tech companies, energy companies, but then they kind of aggregate, and they find it's kind of across the board. It's about this it's being reliable, keeping promises. It's about being open and transparent and behaving responsibly. But that when you look at the importance of these different features, that varies by country. So just to pull out a couple of those, this importance of being open and transparent about what it does in terms of making an assessment of how trustworthy an organization is. So that comes out at the bottom for China, but near the top for Italy. But if we're talking about whether a company is reliable and keeps its promises, there, China's very high up, whereas Italy drops right down. And so you can see this kind of pattern across the board. And we asked a similar thing around genomic data and found some kind of interesting clusters as well of the way that countries tend to come together. But essentially, even if we can identify, I think, the qualities that would be associated with a trustworthy organization, we may have to revisit them from context to context. We did a study over a couple of years around, actually, it was around the use of wearable data for the early detection of dementia. And as part of that, we did a survey of members of the public about trustworthiness and what kinds of things they would associate with an organization that was using their health data. And one of the interesting things we found was that, so when you look at those people who said that they would trust, so what are the kind of things that are important to you if you're somebody who trusts? Again, openness, behaving responsibly, and being competent and good at what you do are important. But there's some variation among age groups. So, for example, thinking about health tech companies, familiarity was much more important to younger age groups. And those distinctions became much more pronounced when we looked amongst those people who didn't trust. And we asked those people who said that they wouldn't trust health health tech companies, what kinds of things were important there? And here, again, you can see, so for the younger groups, this question of familiarity or competence were really important. But for the older age groups, it was about not being taken advantage of and being open. And those kind of things that we can pull out of those surveys then do seem to map on relatively well to some of the things that we've talked about in policy around trustworthy AI, around transparency, accountability, fairness. They accord with these kind of the value of responsibility, openness, and keeping promises in this survey literature. And it comes out in the qualitative data as well. And I haven't shown a lot of the qualitative data because, partly because the quant data makes nicer slides, although I am kind of by background a qualitative researcher. But the kind of importance of these different things varies in terms of their domain of application and the socio-cultural context. Okay, finally, in my kind of last minute, what I've thought about so far is the kind of question of who's trusting whom, and what kinds of things might we associate with trust. But there's a couple of problems with that approach. One is that we tend to treat it as kind of as distinct parts of a relationship. We've got the public over here who trust certain people. We've got the tech companies, we've got developers over here who embody particular qualities. What we're not talking about is the interaction between them. And if there's no interaction between them, then there is no relationship of trust. And whether you can ever kind of disentangle that relationship is questionable. So that's where I wanted to just draw on one final account of what it means to be trustworthy. And this is an account of trustworthiness that's developed by the philosopher Karen Jones. But it's about being counted on and about being responsive. So it's this idea that a trustworthy person takes the fact that they are being counted on as a reason for acting as they have been counted on to do. And that doesn't matter in that sense. If you go back to the falling over and being caught, it doesn't matter whether you're protecting your table of nice glass or whether you're just a nice person or whether you've made a promise. It's the fact that you catch. The motives for it are incidental. All you have to not be is indifferent. You can't just let the person fall or actively push them in the opposite direction. So that means that if we want to be trustworthy, we have to know what it is that we're being trusted to do, what other people are trusting us to do, what we're able to offer them, and how our social relationships with them may shape this relation. So this is a huge challenge for AI systems. That kind of question of knowing when somebody's trusting you is often an affective and emotional question. So this is in the work that the Center for Data Ethics and Innovation did recently around AI governance. This was one of the members of the public's main concerns about, the AI has no ability to gauge my emotion. But it's also a problem for the AI ecosystem, because essentially the only signals that we have around whether people are trusting us are these massive surveys that kind of basically tell us that if we're in a company, we're not going to be trusted. And so so we don't have effective ways of either members of the public signaling to us that they are putting our trust in them, or us signaling to the public that we are trustworthy. And that's where I think that we need to do more work as a field and in collaboration going forwards. And this is kind of something that there's some work been going on recently around kind of proposals for large-scale global deliberative processes around AI governance. So this idea of bringing experts, bringing members of the public, ethicists, regulators together in a context in which they can learn from each other and have a dialogue, and where that's not a kind of one-off process, but that's something that we iterate and ratchet over time so that we're moving the conversation forwards, and that allows us to understand when and why trust is needed, and when and why trust is not needed, and what actually being trusted involves. It means understanding what are the cues that we, as members of the public, can use to identify when somebody can be expected to respond to our trust. And it means being able to act when we are being trusted, or if we're not being trusted, to understand why that isn't. And that this, I think, really means that we need to have more than just the big surveys, as nice as they are for me making slides. But we need to have this iterative engagement, communication, and deliberation that's not just about educating or informing, although that's necessarily part of it, but it's also about listening and responding. And that, if we can't be responsive, I don't think we can be responsible. Okay, so thank you very much. Just some acknowledgements to our team from Welcome Connecting Science and the Kavli Centre. We're a partnership across the university and the campus out at Hinxton, and our funders, the Kavli Foundation and the Wellcome Trust. Thank you. think we have some time for questions, do we?
So, I guess my question is really related to sort of the narrative around AI, and it's how do you find the public and how they amplify AI, and there's this perception of superintelligence, how that impacts trust and sort of that gap in understanding or that different perception of AI, those challenges?
I mean, I think that awareness of AI is rising. I mean, I think there's obviously the kind of the role of the narratives and the kind of the stories around AI that affect how we engage with AI. Although in a sense that's the same for every area of science and technology. And that it's a kind of problem that we all, and it's both the ways that the public think about AI and it's the way that the researchers think about AI and the way that we as a field use those narratives to approach the problem. I mean, the idea of kind of superhuman AI, for example, immediately takes you into worlds of, superhuman. There's a choice of language and of framings that we take to the public as well as the public bring to us. In that sense, is that? Yeah. Sorry. Oh, I was going down here. Okay.
Thanks for the talk. What I wanted to ask was something I think not tangentially related, but I thought it was absent from the slides. So the slides were full of how we're going to integrate the companies and the developments and whatever with trust. But for me, the biggest issue with generative AI, for example, is the erosion of trust. So things that were signaling for, let's say, thousands of years in society trust, now they are being completely outclassed by the push of a button. So you could have things like that before, but now the scale is totally different. So, for example, scam emails. An easy signal for a scam email would be that it would be badly written or have something weird here and there. Now with ChatGPT, you're done. You can have millions of emails. Or with the images. So my question is, in the circles of the institutes that you mentioned, that you are taking part in, is there any talk about how do we, let's say, secure what remains of the trust between each other in the digital sphere or in the public sphere?
It's a great question. I think it is. So it's not. I think it's a really important question, but it's not one that we are kind of specifically working. I think we are kind of working and interested in the kind of governance space and opposed to the question of the kind of trustworthy actors involved in development. But I think that question about how do we trust the information that we're given, how do we trust the knowledge that we're claiming in that kind of public sphere is it's really important. And I don't know, it may well come down again to the development of better cues. I mean, we're seeing already the kind of efforts to innovate ways of detection and things, but I'm not sure that's necessarily going to be the way forward. I don't have an answer, I think. And if I did, then
and in the UK?
So, in terms of the kind of role of trust in the development or in the development regulation, or in terms of?
Yes. How do you see the people now trusting AI systems, given the difference in their approach to the regulation of AI in the EU states and in the UK, which has a particular focus on innovation?
Yeah. So between the UK and the EU, I think the kind of the policy approach probably hasn't played out in terms of how the general public kind of perceive the technology. I think that the biggest distinction from those kind of international studies that we have, like the KPMG one, is between between Western Europe and lower middle income countries and developing economies, where there's much more caution and much less trust than there is in particularly kind of the Brazil, Russia, India, China. So, yeah.
The final question: can we can we trust the public? Think about the Brexit.
That is a great. That's a great question, because it's one of. So this is at the heart of what of our centre. We want kind of this relationship between science and the public. And yes, there's a big part of like how do the public trust science, but actually, in order to make these kind of wider democratic decisions, we need to have trust in the public, and we need to have formats that allow us to make decisions that are good decisions, which is why perhaps Brexit is not a good example of trusting the public. But whereas some of those kind of deliberative approaches, where you're really giving space to a kind of reasoned discussion, have proven really effective in making kind of good policy and good and legitimate policy. And I think that's probably a better approach than just opening things up to questions that are poorly defined and
Thank you very
Thank
much.
you.
Thank you very much for your thought-provoking presentations. And we have all of the presentations in this session. So thanks for our presenters. And we are going to have our break session. Please come back on 11:50 for the panel discussion. Thank you for coming to this session. Thank you.